Welcome to lesson number 5, example number 4. And they're asking to check the design of example number 3 for minimum reinforcing. And if you want to look at what the ACI code requires for minimum reinforcing for positive moment, I hope that makes sense. Positive reinforcement, when they say positive reinforcement, that's wherever. So if this is your beam, I guess, this would be positive reinforcement, since remember, positive moment makes it smile. When it's smiling, if you think about it, if the beam's looking like that, the top is compressing and the bottom is in tension. So therefore, tension is your positive moment reinforcing. It's going to be in tension, which is where you want it to be, because steel is good in tension and concrete is good in compression. Steel's alright in compression as well, but concrete is not good at tension. So that's the whole reason why you put steel reinforcing bars into beams. It's because it's good to handle the tension, and then you just assume that the concrete doesn't do any tension. So you assume that the concrete does all tension, and that the concrete does all the compression, and steel does all the tension. Alright, so this is more just taking a look at those minimum reinforcing code requirements and following what it says. And if you look over there, it says you have two different things. This is the ratio. It looks like you have 200 over Fy, I'll say but, not less than 3 prime C over Fy. And I hope that makes sense. So let's just go ahead and figure these out. What is our minimum ratio of steel? So 200 over Fy, let's do this, equals 200 over Fy, which we know Fy is 60,000 psi. And you get, let me get my calculator out. And typically, I know in AASHTO, when you have columns, this is the minimum reinforcing for beams and positive moment and positive reinforcing in beams, and usually it's like 1% in columns is typically what you see in AASHTO, which is the highway stuff, which I'm sure is probably similar in the building codes. But let's go ahead and figure out what this is for the beams in the ACI. 200 divided by 60,000 equals 0.003. And that's 3 repeating. And that's the ratio of steel. Now, but it says, but not less than 3 times 4,000 psi square root over 60,000 psi, and that's going to equal 3 times 4,000, 2.5 divided by 60,000, 0.03, sorry, 00316, and that it says but not less than, and it's not less than, it's actually greater than, so this controls. Whenever you see min, you always want to know, go with the highest minimum is what's gonna control. So that's your control. And let's figure out what our actual is. And we know that in example number 3, we ended up with 2 number 10s. So we had what? Let's switch colors. Let's go to pink. So we had 2 number 10s, which area steel equals 2.54, and that's 2 number 10s. And then that's our actual, and we need to figure out what our concrete is. And when I say this ratio, I guess what the ratio equals area of steel over area of concrete. And I should have probably explained it at the beginning. Alright, so this is AS. I typically denote as A steel, area of steel. And I guess I always do that with reinforcing steel, AS. But I guess you could do it with if you just had a steel beam, as long as you know what you're talking about. And that's what some things are confusing. Like I've mentioned in the past, I guess you could say, FY, capital FY, or capital F prime C, since it's capacity, and that's what I would like to do. But in the ACI code and everything like this is how they denote those. And the capacity, like more the yield strength of the concrete is 3 KSI, or the yield strength of the reinforcing steel is denoted as F sub Y 60 KSI. Alright, anyways, moving on. I think I was getting a little confusing there. Alright, so we know the area of steel. What is the area of concrete? And we had a B equals 12, D equals 32. And let's just use BD. B times D can equal the area of concrete. BD. And we had 12 inches times 32 inches equals 12 times 32 equals 384 inches squared. Alright, now let's see what we get. 2.54 inches squared over 384 inches squared. And we should have something larger than that. 0.0066. And let's check and see if they got the same thing. They did it a different way, but as you can see, 0.0066 is greater than 0.0033, which was our minimum. So we're good. We know that the reinforcement used exceeds our minimum ratio of steel, and we're good to go. I guess I'll go over real quick the way they did it. And like in most engineering things, you can describe a lot of things, and you can figure out what you want to do. For instance, I simplified everything to my ratio of steel. This is my actual, and this is my required. That's required. REQ apostrophe D is a common way to say required. And as long as my actual is above my required minimum, I'm good. Now on the other hand, they said, okay, well, my A steel minimum equals, and they said Phi-min, I guess that's not phi. I always get my Greek stuff confused. My minimum ratio times BD. And we said our minimum ratio is 0.0033 with a lot of other threes, but we're okay. Times what, 12? And times 32 inches. And we get 0.0033 times 12 times 32. We get 1.27 inches squared. And that's our minimum area of steel required. So you can do that. You can take it, and that is greater than, or that's our area of steel minimum, and that is less than our actual, which is 2.54 inches squared. So we're good. I hope that helps, and I hope you can see that you can compare different things. You can either compare the ratio, the actual ratio, to the minimum ratio, or you can compare the actual area of steel to the minimum area of steel. Kind of depends what you would like to compare. And as I was saying earlier, it's kind of you can come up with a minimum moment compared to your actual moment, and you can also compare your actual stress compared to your stress capacity to see if, as long as the stress capacity is bigger. So this is how you want to show how it is, but either way is fine. Alright, hope it helps. See you on the next video.